be broadcasting on Skype.
But it's you broadcast
Are you recording or Skyping?
Live streaming.
so the camera is this way, not that way, right?
That's right. Thank you all for coming today and filling up the room. It's my pleasure to be introducing Madison Ball today, who will be discussing his master's thesis work with me over the past 2 years. Madison is a Texan who got his bachelor's degree from the University of Chicago. We first met at the UO field camp a couple of years ago where I taught the Four Craters section, and we pondered out in the field the transition between explosive and diffusive volcanism, where the explosive products are bubbly basaltic scoria to form cinder cones, and the diffusive products are relatively dense, bubble-free lava flows. So it was there that we started looking at and discussing the importance of bubbles in controlling the explosivity of volcanic eruptions. So when Madison came here, he took on a project that looks in much more detail at the chemistry of bubbles in silicic systems, and he'll tell you about that today. Along the way, he learned how to simulate magma ascent, both in the laboratory, using pretty cool apparatus and capabilities that we have here at UO, as well as on the computer. So both of those components to his master's thesis presented challenges along the way, quite finicky. And Madison, through great persistence, overcame many obstacles that arose, as you'll come to appreciate in the next 40 minutes or so. Madison will be presenting this work at the International Volcanological Meeting in Portland this August. I think that the turnout that we have today is a testament to Madison's contributions to the department in terms of his positive energy, and how active he's been as just a very social and delightful person to be around. So with that, I'll turn it over to Madison so he can tell the story.
Thank you, Jim, for that introduction, and thank you all for coming today. So ostensibly, as many of you know, this will be a talk about bubbles, but first I'd like to talk about volcanoes. The background of this slide here shows Panem Crater, which is a volcano in the Mono Inyo crater system in eastern California. Now, about 700 years ago, Panem Crater erupted, first explosively, then effusively, like a Hawaiian-style eruption, but stickier. Now, volcanologists really care about why volcanoes erupt how they do, because whether a volcano erupts explosively or effusively really poses different risks to human lives. Now, getting back to the topic of the talk, let's break down what all these terms mean. So, why do volcanologists care about bubbles? There are a lot of factors that determine how a volcano erupts. There's the viscosity of the magma, which is how sticky it is, and that can control how much the magma wants to fragment and explode. There's the presence of water, which can lead to a steam eruption, as with Mount St. Helens in 1980. But there's also bubble nucleation, exsolution, and growth. And as these bubbles grow, then they can lead to an eruption as you're increasing the volume of the magmatic fluid. So let's do some free association. If you saw this giant ash cloud, what would you think? If you're not a volcanologist, it might be run away, but if you are, and if you're me, you think about Diet Coke, specifically Diet Coke and Mentos. So with our Diet Coke and Mentos, although you can't trigger a volcanic eruption with candy, you can use this as a conceptual model to think about why bubbles, or how bubbles can make a volcano erupt. So in the Mentos, you drop the candy in, and you have very rapid bubble formation, and those bubbles take up more volume than the liquid of the Coke, and eventually that just overpressurizes the whole system and forces all the material out in an eruption. In a similar sense, you can have bubbles doing the same thing in a volcano. But in a volcano, our Coke bottle is much larger. And so when we're looking at volcanic conduits, which is the pathway from a magmatic reservoir to the surface, that can be several kilometers in length. And so you have a huge pressure gradient over that distance. Now, deep in the reservoir where you have high pressure, or in your sealed Coke bottle, you can store a lot of gas dissolved into the melt. And in this case, we're looking primarily at water and carbon dioxide, but you can also store chlorine and sulfur and a lot of other gases. Then as that magma rises, or when you open your Coke bottle and you start to depressurize, you form bubbles as you're lowering the pressure and those gases can no longer remain dissolved in the melt. If you continue to ascend, and if you ascend quickly enough, or if other variables happen, then you form enough bubbles that it actually starts to fragment, pieces break off, and it comes out the top of the volcano as ash, pumice, or pyroclastic flow in an explosive eruption. You can imagine some other history where the bubbles are able to gently rise out, and then you end up with a fairly peaceful, effusive eruption. So studying how these bubbles can form and evolve is really important for understanding what controls how volcanoes erupt. Let's start to get into the nitty-gritty of it. This diagram is commonly used in degassing studies, where volcanologists are looking at how the magma in volcanoes lose their gas. On the left here, we have carbon dioxide concentration plotted, and on the bottom, we have water concentration. And this is concentration of volatiles, or these gas species, dissolved in the melt. So, and then this line here and this line are both isobars. And what these isobars represent are the maximum possible combinations of the maximum concentration of dissolved carbon dioxide and water for a given pressure and temperature. So if we start deep in the earth, about 3 kilometers depth, with a magma, well, deep relative, depending on who you are. So we start at a point here, let's say, and we ascend our magma and we raise it up until it is under 30 megapascals of pressure and is much shallower in the earth. Now, if we want to find out how that's going to degas, it can go many different ways. And it can end up different places on this isobar. So volcanologists often study degassing paths to try to figure out how these bubbles actually evolve. And depending on which degassing path you take, that can have a different behavior for how quickly the bubble grows, or other factors, what the composition of the bubble ends up with, and that's all really important. So let's go into the beginning of bubbles. Bubble nucleation. To form bubbles, you have to nucleate them. And bubbles nucleate when you move far enough away from that isobar, when your pressures drop sufficiently that you just have too much water or carbon dioxide or other gases dissolved in the melt, and it can't hold on to it anymore. And so it has to go somewhere, so usually it forms bubbles. So bubbles nucleate when this critical supersaturation is reached, and there's 2 different types of nucleation we talk about. There's heterogeneous nucleation, which occurs on impurities in the melt, or in the case on the right, impurities in the glass, where the left glass has a lot more scratches and maybe dirt or soap scum in it. Don't think about that last part. Than the right glass, and can form a lot more bubbles because it has these little nucleation sites. And heterogeneous nucleation requires much less supersaturation than homogeneous nucleation. And homogeneous nucleation is where you've gotten so supersaturated that bubbles just spontaneously start forming throughout your fluid. Now, after a bubble nucleates, you have to take that material from somewhere. So when a vapor and melt are in equilibrium, there's no flux between the molten rock and our bubble. The bubble isn't growing or shrinking, chemically at least, with the moles of gas going in. So immediately after you form your bubble, and this is a nice simplified representation of it, you have to take that gas out of the melt and move it into the bubble. So you end up with these little depletions right at that bubble melt interface. Now in nature, generally abhors gradients, and so those are going to start to smooth out over time. And if you allow enough time, the bubble will reach a new equilibrium, where you'll have totally flat gradients in the melt, and the bubble will not be growing or shrinking anymore. And so since we really care about how quickly these bubbles can grow and how that can really affect eruptions and general conduit processes, we are very interested in what this equilibration timescale is. And so we have a characteristic timescale that we call tau for that. Now there's three regimes of bubble growth. There's equilibrium growth, where tau is small enough that it's negligible, and that the bubbles can respond instantaneously or roughly instantaneously to pressure changes. And they're just responding to the new solubility conditions. Then there's also non-equilibrium growth, where you have to take into account the time to diffuse your gases through the melt to the bubble to grow the bubble or shrink the bubble, depending on what pressure changes you're looking at. Then there's also viscosity limited growth, where the stickiness of the magma around the bubble is actually physically restraining it and keeping it from growing in size. But this is a chemical study, so we're looking at the first two. Now, how do volcanologists study degassing? One way is analysis of natural samples. So down here in the bottom left, we have a pyroclast, which is a little bit of obsidian. They're usually about a centimeter in size, so this one is mounted in an epoxy puck. And it has some dissolved water and carbon dioxide in it. And this one's from that crater, or near that crater that you saw in the first slide. Now, if you collect a bunch of these, do the measurements on them, and plot them, you can start to see these paths here. And what this represents if each of these points is a different pyroclast that came from some different depth in the conduit, then we start to construct the degassing history of this magma as it's rising out and erupting. But nature has a lot of scatter, and we really want to understand what the individual variables are that are controlling this system. So we have a couple different ways to do that. The first way is to do decompression experiments. So this is a figure from a study done in 2010, and it's really, when I started my work, the only one of its kind and the only one that I had to work from. And so what they've done here is they've taken a little bit of obsidian and put it under pressure and temperature with water and carbon dioxide. They hold it there until it's fully saturated, and then they decompress it. And when they decompress it, it forms bubbles. And you can see these nice bubbles scattered throughout the melt here, which was then quenched to glass after a few hours. And if you look at these transects taken, so this one here goes to the graph on the top right, and then this shorter one here goes to the graph on the top left, you have water in gray and CO2 in black. Now the water has equilibrated really quickly. This water can move pretty fast through the melt. And so it already has a flat profile again. But even after a few hours, CO2 is still slow to respond. And it's creating gradients in the melt. And if you compare these two profiles with the longer one, you have much less equilibration happening in the same amount of time than with the shorter one. So that's some foreshadowing for what we'll be talking about later in this talk. Another way you can look at these variables is with simplified numerical models. So we do a lot of simplifications to try to make these speedy models. One is we approximate our bubble and magma system as a sphere. So we can just do a one-dimensional cross-section across it. And then we can control all sorts of parameters. We can control the starting water, we can control the temperature, the initial pressure, the final pressure, the decompression rate, the bubble spacing, the bubble size. And this is great, assuming our models are working close to nature, because then we can really start to play with those individual variables and see what their effect on equilibration time is. And what these models look like as they run is you start out with some fully saturated faux digital melt. And this represents a distance between two bubbles. So on each side here, you will have bubbles that are taking gas from the melt.
Are they expanding?
They're not expanding in this case, and I can talk a little bit more about that later. And then right at the beginning, in this case, we're doing an instantaneous decompression. So you drop it to some new pressure, and then you update the melt right next to the bubble to that new equilibrium condition. Then, over time, you let the model start to diffuse, and you'll get these nice profiles, and they'll evolve towards some sort of equilibrium concentration that we define. And when the time that it takes to get to that equilibrium concentration, that is our equilibration time cap. So to review, bubble growth and evolution affects eruption style. And it's really something important that we'd like to study and better understand, because understanding how volcanoes will erupt affects how we construct hazard maps, and we'd like to constrain that. But the chemical evolution of bubbles is highly complex. Even though we have all these simplified models, bubbles can vary wildly across a system, and the conditions can vary wildly across a system. And many variables affect how quickly bubbles can grow. So what did we seek to do? We sought to perform the first mixed volatile continuous decompression experiments and construct a framework for the simple analysis of degassing path style based on fewer key variables to inform conduit models. So let's start with the experimental work. The experiments all start with our capsules. What this is about a 1 centimeter long gold capsule that we fill with obsidian and then some other material to make a water and carbon dioxide fluid. Then we seal it up and weld it, and then we can load it up into our rapid quench cold sealed pressure vessel. I'm sure everybody has one of these at home, but this can hold our sample at high temperatures and pressures for days to weeks to even months if we really needed to call on it to hopefully equilibrate our sample. And then we can do computer-controlled decompression to decompress our sample along continuous decompression paths, multi-step, or single-step. And these decompression paths are important for a variety of reasons. So the experiment I showed you before, the Japanese experiment, was a single-step decompression. They started off at one pressure and then fairly instantaneously changed it to another pressure. We really wanted to look at these continuous paths, and that's important for two main reasons. Continuous decompression will change your equilibration time. As you are dropping your pressure, if you're allowing it to diffuse while you're dropping, then you can get a little bit of equilibration even while the pressure conditions are changing. So that's important to look at. Additionally, your decompression style will change the shape of your bubbles. And changing the shape of the bubbles changes the shape of the melt in between the bubbles. And we'll see later that that can be really important. And also, we just assume that magma is not teleporting to the surface in reality, and so it has to experience that whole range of pressures in between as it's ascending in the earth. We had some problems though. So first of all, gold, it turns out, is pretty soft, and especially under high temperatures and pressures, doesn't like to stay sealed. So our gold capsules often sprung leaks. And when they spring leaks, they lose the carbon dioxide since our pressure medium is water. So you still end up with some interesting things. You can get bubbles with gradients, but if you look at our nice degassing plot, everything just falls down on the bottom. So that's not especially useful for degassing information. We changed some things to combat that. First, we started annealing our capsules at 1,000 degrees Celsius, which had the goal of healing microfractures and then trying to correct some of the manufacturing defects. And then we also started using thick-walled gold capsules, but that comes at greater expense and inconvenience because we had to have them custom made. But that started to work out pretty well. We had even more problems though. So homogeneous and heterogeneous nucleation turned out to be quite an issue. Initially, our samples that we put in our capsules were natural samples. They were pieces of obsidian collected in the field, chopped up into slabs, and put up. And so they have microlights and existing bubbles and other things that can lead to heterogeneous nucleation. And what we found is that led to extremely unpredictable bubble formation. So in this case, these are two samples that were roughly the same material, fairly identical, but they had two wildly different bubble formation behaviors. On the left, we ended up forming streams of very small bubbles, which, while still interesting, didn't provide us the heterogeneously distributed bubbles that we wanted, so we could really get nice transects between bubbles and try to look at those gradients. In another case, we ended up with one huge bubble, and that's also no good. So we switched from using natural material to a synthetic obsidian. It has no impurities in it and will only allow for homogeneous nucleation. Well, as I said before, homogeneous nucleation requires much greater supersaturation. And it turns out we then had problems forming bubbles. And so we tried doing higher starting pressures, which would allow for dissolving more water and carbon dioxide in it, but our pressure vessels just couldn't hold, and we often got leaks with that. So we worked with what we had, and eventually we even did get some bubbles. So here's one successful experiment, we'll call it. And we ended up with gradients of water and carbon dioxide. And so these are all measured by FTIR, or Fourier transform infrared analysis, which has the great benefit of letting us make these area maps here. So we can really look at how these chemical gradients change spatially. And what we found was with water, we kind of got what we expected, and that's great. It's fairly homogeneous across the sample. It has the greatest concentration in the center of the sample, and then you see a little bit of diffusion outwards right at the edges, where it's responding to the new pressure conditions and starting to lose some of that gas. In CO2, on the other hand, we see exactly what we did not want to see. In the center of the sample, we have the lowest concentration, except for where you're measuring the bubble there, but that's an artifact from FTIR. And what we interpret this to be is that we are seeing the CO2 still being equilibrated at the time of decompression, and that even though this sample was held under temperature and pressure for 15 days, it just wasn't enough time to fully equilibrate it. Additionally, what we would expect is if we looked at the edges here for water and for CO2, we would hope that we would see a range of concentrations going from the 30 megapascal isobar all the way up to the 100 megapascal isobar. And that assumption that all the gassing models are built under, it is the vapor melt equilibrium assumption, where we assume that right at the edge there, where the gas meets the magma, that's an equilibrium, and that doesn't hold. So with our equilibration time, we did some calculations, and what we found was that to equilibrate your sample to 90% equilibration, your length that you're diffusing over is hugely important. So our samples were about 2 millimeters in diameter, but we had the problem where a lot of them were getting pushed against one side of the gold capsule. And so they were only diffusing in from one side, and they had to diffuse over the whole 2 millimeters. And combined with lower water concentrations, that led to calculated equilibration times of upwards of 50, 150, 200 days, which is not really good for a 1.5-year master's thesis. So even if omnidirectional diffusion were occurring, if you're diffusing from all around the sample, it can still take dozens of days, which is hard to work with. Now, I plotted the Yoshimura and Nakamura data, and they used a much smaller sample. So theirs were only about 1.2 millimeters in diameter. And they also used a higher degree of water. And that can equilibrate a lot more quickly. But you also then have to sacrifice the area that you're analyzing. And if you have less sample, then you can get less information about gradients. Now, looking at these timescales, it's kind of makes you wonder, how it was thought that equilibrium degassing would always be occurring anyway, since it obviously takes a really long time to equilibrate this magma. Now, looking at another experiment, we see that one-way diffusion very clearly. So in this case, there's the gold capsule. This is in cross-section. Our sample here, and there's this nice little gap there. And what that provided is we just get these concentric rings going away from that gap. And in the top right, it's really unfortunately nice. where the highest concentration of CO2 is right at the edge there, where that would have been interacting with the fluid, and then the lowest concentration is the furthest away. We're not giving up on experiments though, and we have some future directions. So two things we'd like to do are to reduce the equilibration distance and also provide more pathways for the fluid to flow through by using ash rather than slabs. This comes with its own problems. For one thing, if you're using pieces of ash, then all the places between the ash can become bubbles. So you're losing information on nucleation kinetics, and you also end up with slightly more unpredictable bubble nucleation behaviors. We would also like to increase the fluid fraction of H2O, which would just speed up diffusion times. And then both of these things are thought to be probably more accurate for modeling actual pyroclast formation, where you have higher water concentrations. And a recent paper came out that suggests that they are probably likely formed by the sintering of ash. Moving forward though, we had this good experiment to work with. It wasn't our experiment, but that's fine. So they did an instantaneous decompression, and we tested our model against it. And what we found is our model fits quite well. So especially in this carbon dioxide profiles, if we set up the same experiment digitally, we end up with pretty much the same result. The water concentration is close, and it shows the same profile, but it's a little bit off. And we can attribute that to some error in the water solubility calculations and also an FTIR measurement, or a combination of the two. So seeing that our model works pretty well, we marched forward. And we really wanted to find what variables are important for equilibration time. So as I hinted at earlier, the thickness of the melt between the bubbles, or the bubble spacing, changes the distance the volatiles have to diffuse. And diffusion kinetics theory says that that should increase our equilibration time exponentially as you increase the length that the volatiles have to diffuse over. And then the diffusivity of volatile species will also change your equilibration time. So that's how quickly you can move your volatiles over that distance. And that depends on temperature and your water content primarily. And these two things can speed up or slow down how quickly your gases move through the magma. And water content is controlled by your initial pressure, your final pressure, and your vapor composition. And then bubble size will also affect that. So over here on the right, we have two different model setups. In the left panels, we have a model setup where we have 100 micron bubbles that are spaced 100 microns apart. And on the right, we have smaller bubbles. We have 20 micron bubbles spaced 100 microns apart. And if you run the same experiment for both of them, where you're only changing this one variable, you end up with slightly different equilibration times. The left one equilibrated in about 1.7 hours, and the right one equilibrated in about 1.4 hours. So that's how these models look when we're varying just one parameter. Now let's dive into this model and really see how it works. So in the beginning, we start out with a fully saturated melt. Some point on the isobar here that's determined by just our initial conditions. And then we drop the pressure instantaneously. And the pressure drops, and again, right at the bubble melt interface, you re-equilibrate to that new pressure, which has some lower concentration, and then over time you start diffusing. And water can diffuse really quickly, so it vary after only about 1,000 to 2,000 seconds. It makes a completely flat profile, but CO2 is our limiting factor here, and it takes several thousand seconds in this case to hit that flat profile. And then you end up with some final distance for equilibrium. Now if we look at just this point here, known as our far field melt, the point furthest away from any bubble, so that'll always have the highest carbon dioxide conditions, this is how it evolves. So in the beginning, there's a slight flat part where you're waiting to see that signal of the decompression. Then you start to diffuse the CO2 out to the bubbles, and your concentration at that point is decreasing. And what the math-minded of you might notice is this can be approximated by an exponential decay, which is really fortunate, because then we can define our equilibration time as an e-folding time. And that e-folding time is the e-folding of the difference between CO2 concentrations at the beginning and the end, as it reduces by a factor of heat. And that lets us really prepare to make this a very broad model where you can start to reduce everything down to a few parameters. So here's some results of that. So bubble spacing and size both change our equilibration time. What we found is that bubble spacing, or the distance between the bubbles, increases our equilibration time hugely. So this is a logarithmic scale here. So you have 1,000, 10,000, 100,000 seconds on that axis, or 1 hour here and 1 day up here. And changing your bubble spacing by a factor of 10 changes the time that it takes to equilibrate by a factor of 100. And that's really good because that's predicted by diffusion theory, but that's a huge effect. And so we're going to keep that in mind. Then we looked at bubble radius, so the size of our bubbles, and it has an effect as the bubble radius changes how the water content in your melt is interacting with the bubble, and that can slow down or speed up diffusion a bit, but it's not a huge effect, especially not compared to bubble spacing. We also looked at temperature. So temperature controls the diffusivity of our volatiles, and that controls how quickly they can move to the bubble, and that also has a huge effect. So changing the temperature by 100 degrees changes the speed that you can move your volatiles to the bubbles by about a factor of 10. We also looked at starting pressure. And so if you start your pressure really low, then for all these runs, we had the same pressure drop of 50 megapascals. So for this first one, you start at 50 megapascals and then you decompress to 0. Then what's happening is right at your bubble melt interface, you're losing all of that water, and all of that water is coming out, which slows things down right there, and it acts as a barrier to diffuse water and carbon dioxide across, because water speeds up diffusion. But once you have enough water, it flattens out, and it doesn't have an effect anymore. We also looked at the effect of pressure drop magnitude. So all of these runs are started at 100 megapascals, and then we increased how much we drop the pressure. So here, our final pressure would be 100 megapascals, and then over here, our final pressure would be 0 ambient pressure. Not ambient pressure, but close to it. And what we found is the same sort of result, is that if your final pressure is staying high enough, then you have enough water content that it doesn't slow things down. But as your final pressure gets low, it starts to hinder diffusion. Then we also looked at the effect of vapor composition. And so the x-axis here is mole fraction of water. And what that is what percentage water versus carbon dioxide your gases or your volatiles dissolved in the melt are. And what that shows is that as you add a little bit of water, you have a huge decrease in, or fairly significant decrease in equilibration time. But as you continue adding water, it doesn't have as great an effect, and it doesn't matter as much. So quick summary. Initial pressure, final pressure, vapor composition, and bubble size all have effects on equilibration time. Temperature and bubble spacing, or bubble number density, which is the number of bubbles you have in some unit volume, are by far the most important factors. But these were all done with instantaneous decompression, because we really wanted to lock everything down and only vary one parameter to see how equilibration time responded to each parameter. And that's not a realistic representation of magnetic systems. So we also wanted to look at the ascent rate, or the decompression rate. Now, how would that change the model? So with instantaneous decompression, at the first time step, we have this huge valley here, where you've reduced the concentration right next to your bubble to that final concentration, or close to it. With continuous decompression, this will be continuously moving downwards while you're also diffusing. So you have some extra time there to equilibrate. And what we found is that you can vary these parameters and get a really nice equilibration space. So on the left axis here, we have log scale bubble spacing, and on the x-axis, we have log scale decompression rate. And what all these dots are plotted is if once the system reached the final pressure, it was in equilibrium. If it had this curve or was flatter than that curve, then we plotted a black dot, a filled dot. If it was steeper than that curve and above that curve, then we plotted an open dot. And so what we've constructed here is a really simple framework for looking at degassing style based on only two parameters, two of the most important parameters. And what you can imagine is how a magma may travel along this plot. So if you start out, let's say in non-equilibrium, and you're ascending fairly quickly, but your ascent causes more bubbles to nucleate. And so as bubbles nucleate and grow, then you're reducing the spacing between them. And so you'll reduce the spacing, and if that doesn't change decompression rate, then you'll travel downwards. And you'll go transition from a non-equilibrium degassing regime to an equilibrium degassing regime. Alternatively, you can imagine that you start in equilibrium, and maybe you start to nucleate more bubbles, which produce the spacing, but that really speeds your magma up, and it pushes you over to the right, and so you transition from equilibrium degassing to non-equilibrium degassing. And the same thing is plotted over on the right, just with bubble number density rather than bubble spacing, but those are fairly equivalent parameters. Now, why do we care about equilibrium and non-equilibrium degassing? So as we've been talking about before, the degassing style influences bubble growth, and it can really control how quickly those bubbles can grow and influence eruption style. But degassing style also controls what the composition of the gas coming out of the volcano is. And we use volcanic gas emission monitoring to try to predict when volcanoes may erupt. And so being able to interpret accurately what these gas emissions mean will really affect how we read that information. So the assumption that equilibrium degassing is occurring will depend on many variables, but bubble spacing or bubble number density and decompression rate are two of the most important. So in conclusion, what I did was I quantified the effect of several variables on equilibration time and found that temperature and bubble spacing have dominant controls. I predicted under what conditions equilibrium and non-equilibrium degassing would occur based on bubble spacing and send rate. And then I also performed the first mixed volatile continuous decompression experiments and laid the groundwork for future experimental work. So that's the science part of my talk. Now I'd like to do some acknowledgements. First, I'd like to thank my lab, Jim and Marissa and Ellen and Aaron. You've all been wonderful, thank you. And my committee, Paul and Jamal, always such a help. My family, thank you to my sister and mother and grandmother for traveling out, and hi Dad. And then Julia and Watson, thank you for always supporting me. And really, I'd just like to extend a huge thank you to the department. You've been such a wonderful community, and I've been lucky to be here. Thank you. Any questions?
Still the bubble expansion, how important it is if a single bubble expands?
So, that's a great question. We didn't take bubbles expanding into account. And as bubbles expand, you would expect that they would deform the melt around the bubbles, which would generally reduce the spacing between them and change your equilibration time. Now this plot on the right shows bubble number density and decompression rate. And our line in between the two fields has a slope of about 3/2. And that fits perfectly with the predicted slope by a paper by Gonerman and Menga in 2005, where they tried to look at bubble number density and decompression rate's effect on bubble equilibration. And their code is a lot more advanced than ours, but it's a lot heavier and can't be run as many times. But they found the same result, and they do take bubble expansion into account. So that was a nice finding that it seems like even though our code is simpler, it provides pretty much the same result.
So what happens in the code between equilibrium and non-equilibrium degassing? So what does that line correspond to? Is that like a dimensional number of some sort, or?
Right, so each of these points represents a model run. So we ran the model several hundred times. And what this line is it's just a boundary. So we just put that in to separate non-equilibrium and equilibrium. And that's determined by the final conditions once the final pressure is hit. We check whether our system, once we fully decompressed, is in equilibrium or not in equilibrium. And if it's in equilibrium, we plotted closed point and open if it's not in equilibrium. Am I missing your question?
Well, so what is equilibrium? Equilibrium between what?
One of those curves that you showed before, it still matches that curve, or flatter than that, that's equilibrium, right?
Yeah, so right here,
And then we feel
equilibrium is equilibrium between the magma, between bubbles, and the bubbles. And so when you're in equilibrium, you would expect to have a flat profile for carbon dioxide and water. And we're using carbon dioxide as our equilibrium timescale because it's the slower diffusing species here. And so we define equilibrium to be this condition marked in red here, which is the e-folding time for the difference between the initial carbon dioxide and the final carbon dioxide content.
So can you show again the two plots with your results, the model results?
Yeah.
Yeah, this one, yeah. So where would the typical linear evolution be on this plot? What is typical government density for like any crater, for example, in premises?
So that would be a huge range. So depending on your history, and then decompression rates are often not very accurately known. But I think you could plot pretty much all over here. Usually pummices are in the 10 to the 12th bubble number density.
2, 3 others are probably even more.
More, yeah.
14, 15, sometimes 16.
Yeah, so I think 10 to the 11th corresponds to about 100 micron spacing between bubbles. So if you're having pumices that really just have thin melt shells between them, then that would be 10 to the 13th or more. So then that would really expand your equilibrium degassing regime. So this would probably be more useful than for slower ascent, and then also, well, slower or faster ascent, and then also deeper conduit systems where you haven't fully fragmented and haven't formed all those bubbles yet.
And that is for given bad chemistry, right? This is just for rhyolite.
Yes, this is just for rhyolite, high silica, for our certain pressure and temperature conditions. But one really great benefit of our code is it's pretty lightweight, so you can quickly vary the parameters and construct new parameter spaces to make this for different temperature, for instance. Unfortunately, making it for basaltic melts will be tough because a lot of the solubility relationships are not quite that well constrained yet. Not as well constrained, at least, as the silicic melts. Bart?
So how important is heterogeneity in the magma?
Heterogeneity how? In what respect?
Like in actual magma, or I guess actual pumices or whatever.
Sure. Like chemical, bubble
Are the-
spacing.
Well, I was thinking like how uniformly distributed are the bubbles?
Yeah, so that will be hugely important, and especially with thinking about all the things that happen as magma ascends, like towards the boundaries, you'll get shearing, and you can create vapor pathways, so you're not even diffusing into bubbles, you're diffusing into channels of vapor. That will change things. So what this is for starting to expand the smaller scale to look at the large scale. So our, let's see, nope, wrong way. Our simplified model with our hexagonally close packed bubbles way back there. Even further back than I thought. Here. So this is how we approximate our bubbles. And then with our hexagonally close packing assumption, we assume that this is sort of repeated throughout the system and that we can treat each bubble identically, but that's not really going to be a good assumption in real life. So the actual scaling of this will depend on your system and how heterogeneous it is. And it also depends on what is actually heterogeneous. As we saw, different factors have different effects on equilibration time, so you might be able to ignore certain things.
Would it be easier to add a line in the code which will allow you to renormalize the growing bubble, just spacing?
That's
it seems like very easy.
Extremely difficult actually, because then you're changing. You actually have to deform each node, so you're changing the geometry of it, and as you grow each bubble, you get thinning of each packet of magma, and I tried to add bubble growth to it, and it did not work. Ben?
I may miss something.
Okay.
But I want to know what properties of water decrease that equilibrium time.
Sure. So if you add a little bit of water to a melt, you start to depolymerize the melt. So if you think of the silica as big sticky chains that are all sticking together, a little bit of water just loosens that up. But adding more water doesn't do that much more. So if you add a little bit of water, you decrease the viscosity by a lot, and you can increase the diffusion rate by a good amount too. Alan?
That's a really nice talk. Thanks for
Thank
that.
you.
Question back to your experimental work.
Okay.
Was there any like physical limitation or something with the apparatus that limited you to going to higher temperature to speed up all of your equilibration time?
Yeah, so we were running all of our experiments at 800 Celsius, and really that oven shouldn't go too much higher than that. Probably 1,000 would be its highest limit. It was really the pressure that was the limitation. We wanted to dissolve. Well, one effect that we would have, I can use my supplementary material to help this out. If you increase the temperature, then you're going to decrease the amount of, here we go, of water and carbon dioxide you can store in there. So that would help by just lowering your final saturation conditions, and then also would increase the diffusion rate. But then we run into more problems with bubble formation. And so it's balancing equilibration time with the amount you're actually saturating your melt to try to be fully equilibrated, but also to be able to have enough change in saturation, enough supersaturation to form bubbles homogeneously. David?
You might not know this, but in the picture of the Samuel's experiment, Japanese book,
Mm-hmm.
can you please show it me?
Yeah, of course. Nope, wrong way. Sort of. So what's this one?
Yeah, so if you look at some of those bubbles, they have glass inside. What do you think that is?
Are you talking about this light part here?
Yeah.
I think that's just a visual. I don't think that's glass. I think that's the bubble itself reflecting light.
Oh, okay.
Yeah.
Then I have a second question. So I might have not gotten this straight, but during the continuous or stepwise decompression, equilibrium time for CO2 is 0 to 1, right?
Equilibrium time can change based on a number of variables. So it can be really long or it can be.
But in one of those plots that you showed and you said, oh, this is not enough time for master experiment.
Oh,
With the light limit is.
let's see, which one? This one?
Yeah. I'm sure I'm getting this right, but does it have any implications for medicine? Like, she uses CO2 in the entrance and the equilibrium profile, but if it ascends like fast enough, then
It absolutely has a connection, but I trust Madison has put some good thought into it.
True. I mean, most of mine are less than 500 microns. So
Yeah.
the things he's using are larger than my crystals are. So I think that helps for sure the length of it that you're actually maintaining it. But if you start sending it too fast, then yeah, you do get into the disequilibrium thing. That
Madison, how are you? Lizzie?
Sorry, I'm not a geologist, but I'm wondering, would your recommendations for future experimentation be centered around the use of ash particles rather than those full pieces?
Yeah, so we were using full slabs to start with, where it's just one piece of obsidian. I tried a few where I also broke up the slabs into 2 or 3 pieces. But I think ash particles are where we're going with this, just partially because of the focus of how the field's turning. So Jim and then also another Jim down in Texas and some other scientists have been really studying how this ash sintering works and how the pyroclast formation can be linked to ash sintering. And so the ash poses some problems, but it would also provide a lot of new interesting information. And if it works well, then we could get some really nice gradients between bubbles and things. And that's really our end goal, is to with the experimentation, we'd like to get the Yoshimura-Nakamura style gradients and start to use that to apply that to natural samples in the gradients we see there. Bart again?
So I don't know if you can actually tell this from the experiments, but when you decompress the magma, do the bubbles all nucleate at the same time?
Yeah, so that's one of the assumptions we make, is that bubbles nucleate instantaneously, which is certainly not correct, because especially with our homogeneous nucleation, you have to hit that supersaturation overpressure, or that supersaturation level before you actually nucleate the bubbles. So that's something that is an endemic assumption in all these sorts of experiments, and it would be interesting to look at how that actually affects equilibration times.
So talking about that, so you made some experiments where you could not nucleate any bubbles.
Yes.
So what were the conditions of this? Like the initial pressure?
Sure. So this one was one where we did not nucleate any bubbles. So this was equilibrated at 100 megapascals and 800 degrees Celsius for 11 days, or 12 days, and then decompressed to 30 megapascals at 0.01 megapascals per second, and that takes about an hour and a half.
So
And then it was quenched instantaneously.
why did it not nucleate?
So we think it didn't nucleate because there's a paper, it's at the Figa and Sishi paper, where they do a collection of decompression experiments, and they talk about the bubble nucleation kinetics. And it seems like 70 megapascals is right about the overpressure required for homogeneous nucleation. So I think we were probably like just on the cusp there of consistently making bubbles, but we just needed to get the pressure a little bit higher to start with and get a bit more overpressure.
So you needed more initial pressure.
Yeah, more initial pressure.
So does it mean that if you put a reality plug at 3 kilometers and you're ascending it slowly, you cannot actually erupt it?
Well, in a natural melt, we'll have lots of microlights and other things, and so the heterogeneous nucleation, as we saw with this one, and as well with this one, this was another heterogeneous nucleation, it's actually really easy to form bubbles. It's too easy to form bubbles. You can form bubbles all over the place. And so I don't think there's any worry with natural melts not erupting due to nucleation. Aaron?
You changed the temperature.
So the temperature we picked was determined to match the monocrater system from iron titanium thermometry and also the glass transition temperature. So, sorry, what was your question about?
If you get lower or
Yeah, so increased temperature would increase the equilibration time for two reasons. One, you would be dissolving less material into your melt, and then also the higher temperature would just increase diffusivity, so you would have lower equilibration times across the board.
why does tau depend on bubble size?
So tau depends on bubble size because of a vapor buffering effect. If you have a lot of water already in the bubble by mass, then it ends up taking more water out of the melt when you do that decompression, so it can stay at the same vapor composition, and so you just end up depleting the melting water more right at that boundary, and you get that slowing effect there at the boundary. You have a question, Alan?
I did, but I'm debating if I should assume my question. Still think about it for a minute.
Okay.
I'm not going to, but okay. So, what is your gut feeling? I mean,
Love these questions.
From the standpoint of somebody who's interested in pre-eruptive degassing signatures from volcanoes, right? They used to interpret activity. What is your opinion on whether non-eruptive degassing is ever in equilibrium in terms of that, the gas that we actually measure, the surface being in equilibrium, right? So magma, body, and that.
So sciencing from the hip, I think you can construct a lot of scenarios where non-equilibrium or where equilibrium degassing would be occurring in non-eruptive scenarios. Because if you have a non-eruptive event, I would assume that it's probably ascending pretty slowly. And if you are ascending slowly, then you have a lot of time to diffuse out your volatiles and smooth those gradients. Now, if you had slow ascent punctuated by maybe short events of fast ascent, or maybe some sort of quick bubble nucleation happening, like with Leaf's work with rock falls into magmas creating seismic waves and seeing how bubbles interact with that, then maybe you could get some sort of weird punctuated non-equilibrium event. And if you're monitoring your gases, you may want to be able to, may want to keep non-equilibrium in mind if you see weird events like that, just to try to read it correctly. But I think generally in non-eruptive cases, you'd probably be in equilibrium, would be my guess. Ben?
A follow-up question on Ilya's bubble expansion and leveling.
Okay.
Would finite element or finite volume have any advantages to solving that issue?
So I'm not super well versed in the different numerical models. This is a finite difference model. I looked into some of Chris Huber's and Olivier Bachman's coding, and their sort of mesh grids, and that would be great, but that just requires a level of coding that I have not attained yet. Okay, I'm going to cut the questions off there.
Well, I think the number of questions is a testament to the clarity of Madison's presentation, so let's thank him for...
I don't think that kind of came out how you wanted it to.
Great job. Clarity results in a lot of follow-up questions that people are interested in.
That's all. That's what I meant.
Yeah, no, great job. I figured that. Okay. That was a great presentation.
Yeah.
Can you put your diagram up again that has the bubble number density versus decompression?
Yeah, that is the juicy.
And all the points. I think I just saw something. Yeah. Okay. Good.
You have a,
Yeah. No. I think I just saw something. So you use published facilities for water and CO2 in your model?
yeah.
Okay, so the degree to which they fit that published set of profiles is some validation